I really appreciate the chance to be here. I don't know that we need a new path to quantum logic after that talk. I think it's all sorted out. But I'll give you a couple other alternatives, I hope. An outline for what I want to talk about is here. I want to first ask the question of, do we actually need molecular quantum logic? You're an open-minded crowd. This is a safe space. Everybody's going to say yes. But I think the answer is a little more nuanced, especially if you hang around with like real ion trappers. And unfortunately, I've been doing that a little bit. And so I've had to sharpen my argument a bit, and I'll share that with you. Then I'll tell you what one idea for quantum logic that I've been working on with Wes Campbell. After that, I'll tell you a little bit about our work taming molecules, molecular ions. And then I'll switch over to two, I hope, forward-looking things. One of them is that spam is hard. Now, James knows what spam is, but the rest of you may not. Spam is state preparation and measurement in the ion trapping lingo. And this is what James just showed us how to do. It's hard for us. The way we do it right now is destructive. We'd like it to not be. And so there's a couple ideas for how to get around that. And then at the end, I'm going to briefly talk about something I'm getting really excited about, and that is a new type of quantum logic that we're calling dipole-phonon quantum logic. And I've been working on this with Wes Campbell and Dave Patterson. All right. So, all right, bear with me on this. This is a lot of words, but I'm going somewhere with it. So the dipole-dipole interaction provides a strong, long-range tunable, anisotropic interaction between molecules. It leads to many novel and exciting phenomena, quantum computing, quantum simulation, as said by literally everyone in this room at some point. All right. Well, let's ask the question, is this actually important? Right? Because if you hang around with ion trappers, what you'll find out is, look, these guys for some time have had plenty of lattice spin models. Right? The monopole interaction in an ion trap is much longer range than a dipole-dipole interaction. Right? When you add phonons, it's now anisotropic. In principle, you can pick every one of these J's, so you can make any model. Right? I mean, at least that maps onto like an Ising spin like this. And they're doing it, right? So is there anything left for us? And also for quantum computation, I mean, they already have quantum computers, right? This is something very recent done on one of the IonQ machines where they're estimating the ground state of the water molecule using some of these variational algorithms that were developed in the Harvard chemistry department. So, what's left for us? Well, I think there's two or three things that are important. One is you obviously want a diversity of these models. You can't do everything with trapped ions. That's an easy one, right? But one I think that's more subtle, and it's debatable, but I think it's important, is that this equal sign is really an approximate sign, right? And so if we want to get to the point where we show real quantum advantage for a simulation, right? So you're going to be in a place where you can't simulate it classically. All these sampling methods to sort of validate it are hard. Like, who's to say that the phase transition you're seeing is not because you left out some counter-rotating term, right? And that's sort of what's driving everything. And that sounds kind of dumb and small, but the whole point of quantum simulation is to get to that regime. So I actually think like in 5 or 10 years, that's going to be really important. And so as you'll see with molecules, they sort of give you these Hamiltonians with a smaller approximate sign there. And the things that you're approximating are different. So it's a nice way of validating quantum simulation. And for me, after hanging around these ion trappers, I feel like quantum simulation is the thing that I'm going to get to see over my lifetime do something cool. So I'm kind of excited about this. For quantum computation, the sort of dirty truth of this is that this is done with like 6 qubits, right? So these things are like have super high fidelities, all the gates are worked out. We know we need thousands of qubits to run the surface code. So why do they have 6 qubits, right? The answer is that the monopoles and phonons, which are the things that you use to build a quantum computer, are a complicated marriage, right? The phonons make the whole thing work, but they also kind of get in the way. And they get in the way in 2 ways. One is if you want to build one of these registers and say, here's like, I think this is, we were trapping 8 qubits. The normal mode spectrum that you're using for the simulation or the computation starts to get more and more crowded, right? There are n normal modes along the axis for n ions. So you keep growing the qubit number, it just becomes a harder control problem. That's sort of generic to a lot of qubits, so maybe you just have to learn to deal with it. But you may want to say, well, let me just forget about that. I'm going to take my ions, put them on a chip, shuttle them around, and do sort of, pairwise entangling interactions so that I don't have to deal with mode crowding. Well, when you do that, there's this unexpected problem called anomalous heating in the field, where the ions near a surface heat up faster than they should. They actually heat up faster than blackbody says they should, which is a pretty profound statement when you think about it. And although a lot of progress has been made on it, it's certainly not a solved problem at this point. And so I'm sure James and I will be at NACD, which is this North American ion trapping conference in a few weeks. I don't know if any of you will be there. If you're there, you won't hear me say this, but I'll say it here because this is a safe space, is that these phonon modes are sort of the weak part of trapped ion quantum computing. It's the Achilles heel. So it would be really great if we didn't have to depend on phonons to do things. We're simple people, so why don't we just try to replace monopoles with dipoles? Right? And so here's a picture from our lab of, I think this is 5 barium ions. And here are 2 barium chloride molecules. And the hope is to now use dipole-dipole interactions somehow to do quantum logic. Well, you know about all the different dipolar quantum logic schemes. The problem is that in the ion trap, they don't just natively port over. If you think about the scheme that Dave, who's sitting up there, proposed almost 20 years ago now. What's that? Oh, sorry. Almost 20 years ago now. Because the ion traps trap ions at the electric field equals 0 point, they actually don't have a dipole moment, right? So this dipole-dipole interaction doesn't work that way. If you want to do some sort of Lucan type experiment or blockade type of entangling gates, these things are a little too far apart. I mean, the closest you can get them is about a micron if you work really hard. And maybe that's okay, but you'd really like to be in the 5 or 10 micron range. Okay? And so working with Wes Campbell, who I think a lot of you know, we tackled this problem and I think have a nice solution to it. Around the same time, Conquin, Till Rosenband, and David Grimes proposed something really similar. It's like the same thing, really, for neutral molecules. Right. So how does it work? There's a lot of different ways to see it. I like this one the best. So imagine you have 2 molecules sitting next to each other. They're in an ion trap. They're in, say, the J equals 0 state. Right. So here's the wave function of J equals 0. I'm going to assume the blue atom is super heavy and the red atom is light. And this is just the distribution of the red atom around the blue atom. Right. So J equals 0 looks like this. I come in with a pi/2 pulse, and I make a superposition of, say, J equals 0 and J equals 1. Right? But that superposition is not an eigenstate, so it's going to evolve. And what I get is that the dipoles are just flopping back and forth, right, at the rotational splitting. But they're flopping back and forth in phase, so they rectify the dipole-dipole interaction, even though they're in 0 field. And so that means when your next pi/2 pulse comes in, what you get out depends on the delay time, right, of your Ramsey sequence. You accumulate some extra phase because of this interaction, and it's really easy to just prepare a Bell state like this. Okay? Now, what's exciting about this from our point of view as ion trappers is that this Hamiltonian, which you can write as just a simple spin exchange Hamiltonian, here these Pauli operators are just on the sort of the SU2 of the 2 molecule state. To first order, it doesn't depend on the phonon number at all. You have to go to the second order to see that. And so it means it's really insensitive to temperature. In fact, this is a simulation we did for, I think it was a CO plus molecule. If you just look at the red curve, it's just for when the microwaves are along the trap axis. This entangling gate fidelity, even at a Kelvin, is several nines. Maybe even, it's not certainly not 4 nines, but it's at least 3 nines. Even at 2 Kelvin, it's not so bad. Right? So to contrast that, ground state cooling is like, way over here, right at equals 0. So this makes things so much easier that you could imagine going back to this chip trapping idea where you have molecular ions, you shuttle them around, you bring them together to do gates, and then you have different, zones for readout. What's sort of, I think, exciting about it is if you pick the right molecule, you wouldn't even need any lasers. As long as you can do the readout without lasers, you could just do this whole thing at dilution refrigeration temperatures, which would be a pretty big simplification. Okay, so that's sort of the why we need quantum logic with molecules and one way of doing it. Let me tell you a little bit about what we've been doing in the lab, and that is trying to get a hold of molecules. So we want to move from atomic ions, which are kind of these little spheres, to molecular ions. You guys all know these things can vibrate, they can rotate, and so they're just sort of a harder cat to tame, if you will. They're sort of petsladies.com. There's sort of four things you have to do, right? You have to get the motion, the vibration, the rotation. But these molecules, and especially in our system, we have to worry about them reacting. So we also have to be able to control the chemistry. I'm not really going to talk about the first three. Well, actually, let me first introduce the system. All right, so how do we do this? So we do something that we call the motion trap. We take a magneto-optical trap and an ion trap. We stick it together. It spells motion. And the idea is that, you just use sympathetic cooling, just like ice in a drink, to cool down our molecular ions, right? Pretty general as long as things, don't misbehave. What it looks like with a little more detail is here. There's a linear Paul trap. When you zoom in, when it's on, we use a calcium magneto-optical trap as our ultra-cold atoms. We trap different ions inside of this, and here's a picture with some barium ions that are laser-cooled into a Coulomb crystal. Now, when we're loading in molecular ions, if you can see this, we are left with the following problem. So I think these are some ytterbium ions, and here's a couple molecular ions. You can't see them, right, because they're not interacting with the laser, so how do you know what they are? Likewise, we actually deal with a lot of chemistry in our group as well, and so we often are faced with the problem of we have some trapped ion cloud, and then we have a reaction where you see one of the ions became a molecule that we can no longer see. So how do we identify these things? And we need to do it in a way that's very general, because you never know what you're going to get when you're doing chemistry. So Stephen Showalter, who was an undergrad with John Doyle, I think, and Christian Schneider, who came from Max Planck, these guys did a sort of wonderful job integrating a mass spectrometer into an ion trap. And so what we can do now is at a push of a button, see every ion in the trap, at better than isotopic resolution. So this has been a really big tool for us, and we've actually built, I think, 10 of these things now for other groups. They're pretty useful. Okay, so with that system, we've been working on sort of taming this cat, and to date, we've sort of got control of the center of mass motion and the internal states. The internal states cooling came first. A few years later, it was Svetlana and Thierry Stokelin did some really brutal calculations to explain it all and to show that it's actually a very general effect, that you're going to get really good internal state cooling with ultra-cold atoms and molecular ions. The motional cooling was actually in some ways a lot harder, even though it seems simple. If you think, put one ion inside of a buffer gas, what temperature does it go to? Turns out it doesn't go to the buffer gas temperature because this is an ion trap and everything's harder. If you put two ions, it goes to a different temperature. If you put three, it turns out that there's two answers. It depends on the initial conditions. And so these were some open problems that went back to Daymel, actually. But over time, we were able to solve them, and we could sort of, we don't need to go in detail here, but you could see that the blue points, this is ion number, are if you prepare things cold. The red points are if you prepare them hot. And in this instance, you see this sort of bifurcation that happens, and then these things close. But all that's sort of worked out now. And so what we've been doing over the last year or so is getting control of the last thing, and that is the chemistry. The system we mostly have been working with is barium chloride molecular ions in our calcium lot. The reason we chose this is because all the products of any of these reactions are at least 7,000 Kelvin higher in energy than the ground state. So, by design, we've precluded these ground state reactions. But, you know, if you're astute, you say, wait a minute, I can see this calcium mott, right? We have lasers on. And so that means that there's some calcium P state around. It turns out we really want to leave these lasers on because of these heating effects I mentioned earlier. You want to have some continuous cooling. So, you know, there's really just no way to make these excited state channels be closed. They're always going to be open for any combination I know about. So that's a little scary. And what's even scarier is this excited state has a quadrupole moment, right? A P state can support a quadrupole moment. And I think most people know about Langevin capture theory, like ion-induced dipole, C4 over R to the 4. You get a rate constant that's just flat in temperature. It turns out for ion quadrupole, it's even worse. It just screams up as you go to low temperature. And so this could be really bad for us. The colder we go, the faster our ions go away. And so we worked on this problem. Pratik and Mike are two excellent grad students. Sadly, Pratik is defending on Friday. It's too soon. Robin Cote, I think many of you know. You guys, some of you may know Arthur Suits. He's an amazing physical chemist. So we went to measure this, but we wanted to do a really good job of this. We wanted to be able to really see these features. And if you've done any sort of chemical reaction measurements before, you know that you always have some velocity distribution, right? You have some temperature, and you have to average over it, and it really just dulls any features that you're looking for. So we spent some time developing a technique that we called ion shuttling, so we could look at collisions as a function of energy and not temperature. And the way that works is, as James mentioned, you have these end caps, and you can just put DC voltages on it, and when you do, you can just move the ion back and forth. So if you do that with a mott in the middle, and you construct a waveform so that the ion goes through the mott at a single velocity, you can look at reactions as a function of energy, not temperature. Now, this sounds easy, but James can tell you it's a giant pain in the ass to do this with ions, because you start shaking ions and they heat up. And so we spent a long time designing waveforms to do this. We wrote the most boring paper I've ever written in my life here. But if you need to do this, it's in there, not how to do it. It's boring because there's so many technical details. But you can do it, and the results are actually pretty cool. So here's a picture of us shuttling one ion back and forth through the mott. You only see it at the endpoints because it spends most of its time there. You can do this with a chain, and in fact, we can even implant a molecular ion in the middle and hold it there and shuttle it through so we can look at molecular ion chemistry sort of one by one. And you can even do it with more complicated geometries. So when you do this, here's what you see. There are two P states in calcium that you have to think about when you're running a calcium mott. One is this long-lived the triplet states. What we see there as a function of energy is that the reaction rate, in fact, just screams up like you would expect. The theory is sort of a band because there's some uncertainties in the quadrupole moments. And so this is a little scary. But we can actually repump out this state, so we don't worry about it too much. The state we really worry about is the singlet P1. And interestingly, that guy departs from this ion dipole capture and goes to 0 as you go to low temperature. So why is that? Well, because we've developed this apparatus, when you're looking at a chemical reaction, one of the first things we often do is look at the products to try to figure out what's going on. So we could dump this into the mass spec, look at the products. We can see the calcium chloride, the barium products, and we can measure the branching ratios of this. And those are shown in blue for the three different molecular ion products. What's shown in red is what's called phase-space theory. So phase-space theory is basically just state counting for the number of product states, right? So you're assuming all the product states are equally likely. With the subject of angular momentum has to be conserved, right? So you count all the states you can access by energy, but make sure that you can reach them given your incoming angular momentum. And so you do that, and you see actually really good agreement with the data. And so what that suggests to you, these branching ratios are statistical, means you have a really long-lived collision complex. Right? And then you start thinking about how long is that, right? So it lives for a long time. So like these, these three atoms come together and rattle around, and sort of just equally find, all possible outcomes. So how long? Well, you could calculate it from sort of, chemists would use sort of, maybe like RRKM theory to calculate sort of the complex lifetime. But it turns out that that's actually a big underestimate because of something we know about in this field. And that is that if you think back, if you think of just an atom colliding with an ion, there's a large Stark shift when the ion gets close to the atom. That's another way of saying there's a C4 over R4 interaction. And they're very different for these two states. So you can only excite this with your lasers at really long range. In our case, it's 1,000 Bohr radii, which is like, miles away. And because you're going so close or so slow, before you get to the short range, these things just spontaneously emit. And so then all of your collisions actually happen on the ground state. And so you're sort of naturally protected from these reactions. So we can include that. And when we do, we see sort of qualitative, if not quantitative, agreement. But we wanted to be sure about this because this is pretty important for us. So we did this in yet another system. So we replaced the molecular ion with atomic ions. They're a little bit easier for us to control because we can laser cool them directly. And you can see here the agreement between theory and experiment is quite good. The theory without the suppression effect is here, and with the suppression effect is here. And we said, well, if this is really what's going on, we should be able to turn this off. We should be able to apply we call it the catalyst laser, to dress the ground state and to dress the atom so that there's an avoided crossing between the ground state and the excited state near a crossing with the exit channel, so that we're sort of preferentially exciting to this upper potential right in the sort of chemistry zone. And when we do that, we see that as a function of this intensity, the rate constant increases. It's reproduced by a simple Landau-Zener model and sort of agrees better with some coupled channels calculations. As a function of frequency, we see similar agreement as well. So this was all done, the coupled channels calculation was done by Svetlana and her postdoc Ming. And I think the paper will come out in a week or two probably. All right, so what does this all mean? Well, it means chemistry isn't inevitable. That, these excited state reactions are naturally suppressed. Now, if you've been in AMO for a while, you sort of know this isn't the first time this has happened. Paul Julian predicted something like this, or treated with Frederick Mies, talked about this in '89. Dave Pritchard, Alan Gallagher, among others, saw these sorts of effects, but in neutral atom collisions. But what's interesting here is, first of all, not everybody believed it would happen for atoms and ions because the potentials are very different. We certainly believed it, or we wouldn't have done this from the beginning. But what I find sort of striking about it is this is actually mattering in sort of the 5 to 10 Kelvin temperature range, right? That's pretty hot. So that means sort of regular chemists have to worry about this effect. And at the moment, they typically don't. All right, so what does it mean? It means this is going to work. We've tamed all 4 things that we have to tame for our cat, right? But we still have this problem of spam. So I'm not talking about it here, but right now we do it with resonantly enhanced multiphoton dissociation. It's a pain in the butt because you have to start over every time you detect, right? And so what we're working on now in this experiment is entangling these molecules with this scheme I mentioned earlier. But we'd really like to be able to do the state preparation and measurement more quickly and without destruction. And so I'm involved in another project with Wes Campbell. We had a great postdoc, Dave Huckle, who's now at Air Force, and a grad student, Justin Christensen, developing a trapped ion qubit that had never been used before. And this experience sort of taught me the importance of being able to do spam well and quickly. So barium-133 is sometimes called the Goldilocks qubit for trapped ions. You may say, then why doesn't everybody use it? The point is that everything's just right about it, like baby bear soup. As Dave Huckle would say, there's only one problem with it. There isn't any. And that's because it's radioactive. It has a 10-year half-life and it's all gone. But you can make it. And if you're careful, you can figure out how to laser cool it and trap it. So we measured all the laser frequencies that you needed and all the hyperfine splittings. and now have this qubit going. And the way we do state preparation and measurement here is with electron shelving. You can, hide the population in some metastable state, and then, look for fluorescence in some manifold. And so you have a bright state and a dark state, which we call 0 and 1. The bright state you see, the dark state you don't, right? Just like what James showed earlier. In barium-133, what you do, and all electron shelving, what you do is you apply your laser and you get 2 histograms, right? So if you get, say, anywhere above 10 counts, you determine you were in the 0 state, and less than that, you determine you're in the 1 state. These histograms are actually really good by trapped ion standards. Our spam fidelity is approaching 4 nines. It's actually the world record by a factor of 2, I think, over what Dave Lucas did for a single qubit. So here the Rabi oscillations basically almost go to 1, right? So that's pretty fun. And so how do we get this in the molecule world? Well, we had sort of with this same gang, we had sort of a little mystery that popped up that we explored that may have presented the answer for us. So we were trapping barium ions, and after like 10 minutes, we noticed they start to go away. And so we have this mass spec. We could hit a button, and we could see that, here's the barium. Out here is what this heavy stuff, or this dark stuff is, and it's barium methoxide, BaOCH3. Turns out that this is a reaction product of barium with methanol. So I guess we had a small virtual leak of methanol. But, when life gives you lemons, you just turn the mod on and see if it reacts. And sure enough, it did. And it made something even heavier. And we scratched our heads for a long time about what this could be. It's pretty hard to get stuff this heavy in our world. We took every laser we had and just kept shooting it into the chamber, trying to blast it apart. And eventually we did. And what we found is that it fragmented into a calcium ion or a barium oxide. And so this thing is a molecule, barium, oxygen, calcium. When I first called up Arthur and said, hey man, I think we got this molecule, it's like an oxygen with 2 metals on it, he made some comment about the California marijuana legalization. Because if you know about chemistry, this shouldn't really exist. There are too many electrons. Right? Like oxygen wants 2 electrons, barium's got 2, those guys are happy. Calcium, the same thing. And so there's sort of, in this case, sort of 1 electron that doesn't know what to do. Turns out the neutral of this exists well. Okay. So it actually turned out to be a very interesting story of chemistry that I don't have time to go into. But the important thing I want to point out is we learned how to make this, we learned what made it, and we noticed that the structure looked like this. This is sort of, I call it the electron on a stick. Right? So this looks very reminiscent of what you want for sort of the laser coolable molecules. And so the idea here is that, these atomic like electrons, you can do this spam detection. And so we have our dream is to get non-destructive spam, like James has, and Dave Patterson, who many of you know, has a great idea for that as well. And so we have a collaboration now. I like to call it the electron on a stick collaboration. With a lot of people that many of you know and maybe don't know, but are phenomenal people. Okay, all right, so in the last 4 minutes, let me talk a little bit about the thing I'm really excited about, and that is this dipole-phonon quantum logic. All right, so imagine you have an atom and a molecule in a trap. The molecule has 2 states that are split by delta, right? So we have some Hamiltonian, delta over 2, sigma z, right? Now, and these are connected by an E1 transition, right? So there's a D dot E term. Now the ion trap has an electric field, right? As we heard about. And that electric field, it's the sum of the ion trap plus the other ions, but you get some, harmonic potential of 1/2 m omega squared, x squared, and there's one of those for every one of the phonon modes, right? And you could just differentiate that to figure out what the electric field is. So you take that electric field, you put it in here, you replace D with sigma x, and what you find is effectively a James-Cummings Hamiltonian that's a coupling between the dipole motion, or the dipole of the molecule, and the phonon motion in the ion trap, right? And so if you get this delta close to one of these omegas, sort of all hell breaks loose. And you can do some pretty cool stuff. For example, one of them is maybe a simple way of doing quantum logic spectroscopy. So imagine one of these one of the normal modes of the ion crystal is somewhat close to the molecular ion delta, the internal state splitting. If I start with this, and this axis is for that trap frequency, which I can control just with the DC voltage. Right? So let me start with it low so that it's below delta. Then my eigenstates here, where I'm going to label the molecule as G or E, and the phonon number as just the number. Right? I have G0, G1, E0. As I increase omega, the energy of G1 just grows because that's the harmonic oscillator, right? It just grows linearly. But when delta gets close to omega, this coupling splits these and the crossing is avoided. So what I can do is start with delta below, or omega below delta. I can ground state cool. And like James said, if I happen to be in the state that I want to be in, and that would be the E0 state, I could then just increase my N caps. And if I do it adiabatically, what I do is I force the molecular excitation to disappear and appear as a phonon. I can then ground state cool, and then I have heralded preparation of G0. And now all I've done is just change an N cap voltage and done laser cooling. I don't have time to talk about it, but there are versions of a Molmer gate, which is sort of the Molmer-Sorensen gate is sort of one of the the crucial ingredients of trapped ion quantum information. Because it's almost completely independent of the phonon number. So there's a version of that allows you to do atom-molecule entanglement. There's an effective molecule-molecule entanglement where you can change from spin models that are basically all-to-all coupling to 1 over r cubed. There's a way to do microwave to atom transduction, which is a big deal in quantum information right now. It's really hard to put a microwave into a trapped atomic ion, sort of coherently. And you may say, if you know about molecules, and all of you do, well, these trap frequencies are never more than 10 megahertz, really. So, molecule splittings at 10 megahertz are pretty rare. It turns out it's not so bad, actually. A lot of omega doublets, it turns out that all the EDM molecules are sort of perfect for this. I think we might first try it in thorium fluoride. It's like almost has everything we want. These L doublets that Nick and others have talked about, all are right in this range, and then there's all sorts of tops, which Dave Patterson knows all about. All right, so with that, I'll end. What I want you guys to remember is atomic ions, those guys can't do it all, and we need to help them. We've been working on how to tame molecules. Spam is hard, but we're working on it, and there's maybe a pretty exciting way of doing quantum logic now using this dipole-phonon coupling. Thank you.
So at the beginning you mentioned about not wanting this multi-crowding phonon,
Absolutely, yeah. So I mean, you're bringing phonons back in. So I say everything in moderation. No. I think that's a really good point. Like my sort of dream is that you have a chip for the molecule-molecule quantum logic, and you use this safer state readout. So you're never dealing with more than a couple.
Do you have an estimate for this? So you're talking about doing this adiabatic ramping across the crossing. What like the size of the coupling is? Like what is adiabatic?
Right. Yeah. So I mean, so omega could get up to about a megahertz pretty easily. So it looks like it's not so hard. Yeah, which we were surprised by.
So for this electron on state molecules you mentioned, seems like it's a byproduct of your ion trap, right? If you want to use this guy in the future, if you rebuild your chamber, fix that leak, repeatable, it's going to expand.
Yeah, we actually added there are these piezo doser valves. They're like super slow, but they have like they can like keep almost UHV on one side. And so now we can create stuff on demand after that. It's pretty cool.
So I'm misunderstanding something.
Probably
This
not.
experiment where you said you wanted to vary the energy instead of the temperature and look at the relative dependence on energy. Why isn't there a thermal broadening of the energy? How do you?
Oh, there is, except we just laser cool it to where it's so small.
I see. So it's just that one code.
Right, yeah. I mean, so it gets you down to say the Doppler limit's about a millikelvin, then you still have a millikelvin of broadening. But the axis here was sort of Kelvin. So it's, yeah. No, that's a good point. I should make that clear.
Great. You say, yeah, please.
Yeah, so what would be a limit in this as a function of energy environment, like can you go to 100 K?
Yeah, we could go up to about 120 Kelvin right now. That is with the waveforms we have. So there's this field of sort of optimal control of like how you like, and if we were to do that, I bet you could go a lot higher. We just didn't.
Because I think if you can go all the way to hundreds of Kelvin and maintain Kelvin resolution, this is a fantastic experimental tool to investigate the interaction.
Right. Yeah, okay.
Or if you people have this vibrational energy, or that's 100 K, right? If you want to explore those kind of vibrational H-bar gradients,
Right.
or those kind of things, and also to really understand the room temperature chemical reactions, you need those kind of very exciting tools.
Oh, cool. Thank you. Yeah. Maybe we'll think harder about the optimal control.
I mean, those collider people, they are trying so hard. So like, they're scheme, right? And they are very scheme.
Well, ions are easier. Like, you're right. Yeah.
So you
Yeah, James and I, we went to the dark side a long time ago. Never looked back. Yeah. Awesome. All right, thank you.
Well, thanks a lot for the speakers.